So we would like to have a measurement for strength. Form is just the shape, direction, that's either positive or negative. But for strength, we'd like to have a number for it. Okay? And we can actually do that. And here's how. What we can do is start by normalizing every point on a scatter plot. So for every single point, we would get a z-score for both of them. Okay? So a z-score normalizes everything. Then, once we have standardized both of the variables, both of them are going to have a mean of 0, which makes sense, right? And you're going to have a scatter plot that looks like this. This is the z-score for height, and this was z-score for weight. Okay? We didn't do one like that. I'm just saying, if you were to take the height and weight and do the z-scores, it would look like this. Okay? By the way, when you do the z-scores, the shape is exactly the same as it was before. All we have done is we have moved and rescaled. Right? So if you were to look at the plot of the original and just look at the points, not where the axes are, it would look exactly like this. Okay? So, how do we measure the strength? Well, what we're going to do is multiply those coordinates together for every single point. And then add them up and divide by n minus 1. And this gives us a measure of strength called R, where it's the sum of all the z sub x's times z sub y's divided by n minus 1. Okay? And that tells us the strength. Now, why is it that that tells us strength? Well, let's think about a couple of things before we write any more. If both zx and z sub y are positive, when we multiply them together, we get a positive, right? If they're both negative, we would get a positive also. And notice with this one, it's pretty clear this has a positive direction. It would make sense that our z-scores would mostly be in the first and third quadrants, because when we multiply those together, we get positive numbers. So whether it's positive or negative kind of makes sense. It also, when we multiply those together, we're going to get better numbers when these are the z-scores are kind of close to one another. If you're one standard deviation off, it's nice if the other one is also one standard deviation off. Okay? So, and again, we divide by n minus 1 for much the same reason we did that when we were doing standard deviation. It just works out better. So this number, you've actually used this number before, maybe even as early as Algebra 1. This is the correlation coefficient. And we always use R for the correlation coefficient. Gives us both the direction, which is kind of nice. You can get the direction without even having to look at the plot, and the strength of the linear association. Now, if it's not nearly linear, if it's a U shape, this isn't going to tell you much. That's an important point. Sometimes students will take a scatter plot that is clearly nonlinear and find the correlation coefficient and go, hey, the correlation is 0.98. This is really close to being a line. No, it's not. Okay? If it's not close to being a line, finding the correlation coefficient isn't really particularly useful. Now, I will say on your homework, they ask you to do it a couple of times, but they're making a point that it's not really useful. Okay? Yeah, don't go, oh, Mr. Davis said I shouldn't do that. They're going to ask you to, and then they're going to ask you, does this really tell you anything? And the answer is no. No. I was just, you said yeah, and I said no.
Describe this histogram. It's not a histogram.
Yeah. Trick question. Gotcha.
Yeah. So, before using correlation, check the following conditions. It's got to be quantitative variables. That's usually not a problem, honestly. It's got to be straight. If it's not pretty straight, and by looking at the scatter plot, then using correlation is not a good idea, because the correlation coefficient measures the strength of the linear association and no outliers. If you've got outliers, not a good idea to use the correlation coefficient. So let's take a look at each one of these. It turns out that each one of these has exactly the same correlation coefficient. And you may go, well, how is that possible? Some of those are pretty clearly not linear. Well, the reason why is that the correlation coefficient only tells you the strength if the association is linear. If the association is not anywhere near linear, then it doesn't tell you anything useful. Okay? Let me point out a couple of things. This first one, is it a good idea to use the correlation coefficient on that? Absolutely. Okay? It's a great idea to use the correlation coefficient on that. How about this?
No.
No. Because you have a very strong curve here. But the correlation coefficient for this set of data is the same as it is for this set of data. Okay? This one, we've got this outlier up here.
So don't use it.
Yeah, do you see how it, I mean, this is a nice line, isn't it?
It's tight.
And then I've got this one outlier that changes the correlation coefficient completely. Okay? How about this one?
No.
I don't even know what
Yeah, what is this point up here called?
wrong. I mean,
High leverage point.
High leverage point. It turns out that when you have one like this, if I moved this point down even a little bit, because these are all stacked up on top of each other here, it would move the line exactly through this point. It would still go through this point, whatever it is here in the middle, but moving this one up or down would change your slope. Okay, moving one point slightly should not affect the slope that much. So again, it's got to be straight, no outliers. Okay? All right. Moving on to page 3. There are only 3 pages, aren't there?
Correct.
Okay. So, correlation properties. The sign of the correlation coefficient gives us the direction of the association. So if it's positive, that means our graph moves up as we move from left to right. If it's negative, our points as a general rule move down as we move from left to right. The correlation is always between -1 and +1. Never greater than +1, never less than -1. By the way, what would it mean if the correlation was 1?
That it's perfectly linear.
Yeah, that your data is perfectly linear. Okay? Notice the correlation treats x and y symmetrically. The correlation of x with y is the same as the correlation of y with x. That's kind of interesting. But it makes sense. Correlation has no units because we used z-scores, which have no units, right? Correlation is not affected by changes in the center or the scale of either variable. So if we change the scale or if we move it, correlation is not going to change at all. Okay? Which is what I was talking about earlier. Your data originally would look a lot like this data did. Okay? Correlation measures the strength of the linear association. It doesn't measure anything worth knowing if it's not a linear association. I keep coming back to that, but that's a big deal. And correlation is sensitive to outliers, which is why we try not to use it when we have outliers. That one outlier can really pull things off. Okay, Quinn and I were having this discussion. Was it yesterday morning or was it this morning? This morning. Okay, correlation does not equal causation. Just because two variables are highly correlated, they have a strong linear association, doesn't mean that there's a causation. Let me give you the example that I gave her. Did you know that in every elementary school in the United States, and pick any other country in the world you want to for that matter, that shoe size and reading level are strongly correlated? That the correlation coefficient is nearly 1. It's a true statement.
The older kids will have
Like as you grow older, your reading level goes up. Yeah, that's fun.
Oh, I
Yes,
didn't even think of it that way.
yes,
I mean, obviously.
there is a variable that actually controls both of those variables. Age tends to increase reading level and increase shoe size. So one of those doesn't cause the other. There's something else that causes both of them. Okay? So anytime things are you have a strong correlation coefficient, that doesn't mean that one causes the other. Okay, I'm going to have to email Mr. Hedstrom. He had a whole bunch of different graphs that showed things that had a strong linear association, and there's nothing.
Can we Google some?
We can if we have time. I seem to remember there was one about Nicolas Cage movies that were released in a given year, and I want to say it was mortgage rates or something. Wow. And there was a strong linear correlation, and it was like, what the heck?
How did that happen?
And it's just one of those things where they just happened to be, the same. So you will read about this at some point about straightening / re-expressing scatter plots. One of the problems we have is that a lot of the way that we analyze, much like with the when we had a histogram, if it's not unimodal and symmetric, we have problems with that, right? So we may re-express it so that we get something that is more unimodal. Okay? we're also, and we're going to spend actually a lot of time, not in this section, but in another chapter, talking about, well, what do we do if the line's not straight? Because we can't do the analysis that we want to if it's not straight. So a lot of times we will apply some function to it. We'll take the square root, we'll take the logarithm, we'll do something like that in order to get data that's now straight. Okay? All right, so just remember not to mix up association with correlation. Association is a vague general term. Correlation is a number. It's a precise measurement of strength and direction of the linear relationship between two quantitative variables. Looks like you're about to say something.
What goes in the blank?
Oh, look for other possible, I think it's lurking variables. Yep,
Lurking variables.
one of my favorite terms.
I'm gonna ask. Are you and Mr. Chance to explain your favorite terms?
Hidden variables. Okay,
Something
there's something else that's going on. And it can be like the one with here, that age affects both of them, or it can be that there's something else that affects the outcome. All right. That is it for that. Let me remind you, though, to get going on your projects. Okay? Yeah, this weekend might be a great time, since you have some extra time at least, to get going on those. Don't put it off. Okay? And if you have questions about something, if you have a set of data, you're like, would this work? Feel free to come in and say, hey, I'm interested in doing this. What do you think about it? And we can kind of go, oh yeah, that'll work well, or oh, you may want to consider something else. Okay?